Today's lesson is 11.2 exponential functions. So exponential functions are written in the form f of x equals a to the x power, where a is considered the base, a needs to be greater than 0, and a cannot equal 1. So we're just going to take a look at how we graph this and then a few patterns of what we see. So if I have f of x equals 3 to the x power, what we're going to do is we are going to actually set up a t-chart. So we're going to have x, and instead of y, we'll have f of x, which equals 3 to the x power. So just like we've done before, what we're going to do is we're going to just put some numbers in for x, and I'll talk about how we actually figure out what numbers to use a little bit later. But let's just start right in the middle at 0, go up a couple, and go down a few. And I want to start actually at the bottom. I'm going to take 3 and plug it in. So 3 to the third power is 27. And then I'm going to do 3 to the second power, which is 9. 3 to the first, which is 3. And then 3 to the 0 power, if you remember, has a value of 1. And I'm hoping you recall what happens with negative exponents. 3 to the negative first power is actually then written as a fraction, 1 over 3. And then 3 to the negative second power is also written as a fraction as 1 over 3 to the second, which is 1 over 9, and then so on. So this is 1 over 27. And all you're going to do is plot the points. Now, some of these points are going to be off the chart, so I don't really expect you to have every single one of those. And some of them, like 1/9, 1/27th, we're just going to do the best we can with that. So 327 is way off the chart, so I'm not even going to show you that. But 2/9, 1, 2, 3, 4, 5, 6, 7, wait, 1, 2, 8, 9, that's up there. And then we have 1, 3, and then 0, 1, and then negative 1, 1/3, and then we have these really small points. And if we connect them, you'll kind of see a few things happening. That we know goes up forever. But what's happening to the left of the graph? Think about what's happening. If I put in negative 4, it's 3 to the negative fourth power, which is 1 over 81, and keep going with that. The number keeps getting smaller and smaller and smaller. And what happens is it will never actually approach 0 nor pass 0 in the negative numbers. Because even if I put in a negative for x, it doesn't really negate the answer. It just, remember, flips it over into a fraction. So what we end up having here is this asymptote. This asymptote right here occurs at y equals 0. It's actually not a part of the graph, but it's important to kind of see that line. I'm going to do the same thing with number 2. I'm going to make a t-chart, and I'm just going to take a few numbers. So we'll go from negative 2 down to, well, actually do negative 3 to 3. And I'm going to start at 3 again. So this time if I have 1 to the fourth raised to the third power, you would get 1 over 64. And then I have 1 over 4 raised to the second power. That's 1 over 16. And then if I have it to the first power, that's 1 over 4. And then 1/4 to 0 power, again, that always evaluates to 1. But watch what happens here. So I have 1/4 to the negative first power. And what ends up happening is this is 1 to the negative 1, 4 to the negative 1, and so it ends up flipping. So it actually ends up being 4. You can guess the same thing happens when I have negative 2. I want to have 4 squared over 1, which is 16. And the same thing's going to happen with negative 3, so you end up with 64. Now again, I'm not going to graph the 64. I can show you that the 16 is way off the graph. Just make it way up there. And negative 1 is at 4. 0 is at 1, and then I have 1/4, and then 1/16, and then 1/64 again. So a couple things I want to show you, or hopefully you can notice with this. Again, there's still an asymptote, and for the same reasoning, the asymptote is at y equals 0. Again, this red line keeps approaching but never is going to touch. But notice the shapes of the two. In number 1, I start low and it goes high. And in number 2, it goes high and then goes low. We're going to come back to that once we see a few more patterns. So just keep that in mind as we keep going. So what I'm going to do with number 3 and number 4 is I'm going to do something very similar. I'm just going to make a t-chart, but keep an eye out for the notation. For number 3, it's 2 to the x minus 3. So remember that minus 3 is within the exponent. So what I'd like you to do is actually pause the video and just do number 3 and 4. We'll come to those bottom two graphs in just a minute. So pause the video, make a t-chart, and then plot your points. And then unpause the video and make sure yours matches up. So let's take a look at number 3 first. There's my t-chart. And you can see when I started in the red, I did -2 to 3. And the numbers I came out with were pretty small. 1/32, 1/16, 1/8, 1/4. And then by 3, it finally got to 1. But that's really not enough to make a good accurate graph. So I added a few more numbers. You can see that in the green. So 4 became 2, 5 became 4, 6 became 8. And again, what I want you to notice, and I did a kind of a poor job doing this, but my red line actually should not pass that blue asymptote. It still has that asymptote at y equals 0. Now, because with number 3, I noticed that my numbers were way too small, and number 4 has a very similar pattern, -3. Again, what I did is instead of starting at -3 or -2, I started at 0. And you can see it still gave me 1/8, and then by 1 I was at 1/2, 2 I was at 2, and then finally I got to 8. So those are what your graphs are going to look like. I'm going to hop over to Desmos, and you might want to too. I want to just kind of talk about some of the patterns. So the graph that we see right here is 2 to the x power. And I want to point out just a couple of things before we start changing the graph around. First of all, there's that asymptote I was talking about. It's coming down to hit the x-axis, but you can see it actually never crosses if we zoom in. We have to get pretty small, but you see how it actually never touched. So it keeps approaching there, but it never goes past that y equals 0. The other thing I want to kind of point out is that notice the intersection right here. It's at 0, 1. And I kind of, just like a vertex, I kind of see our vertex in a parabola, I kind of see as that anchor point. So keep an eye out for that. What I'm going to do first of all is I'm going to take this graph, and what I'm going to do is I'm going to, well, actually just let's make it a new one. Y equals 2 to the x, and then let's make that -4. And look what happened. Basically, that whole graph just shifted down 4 units. And you can see that anchor point, which is at 1, went down 1, 2, 3, 4. So instead of being at 0, 1, it is now at 0, -3. And if I were to change this, I'd add 2. You can see that it went up 1, 2. Now let's put, instead of putting a +2 at the end, let's put it in the exponent. So if I do +2 within the exponent, look what happened. The red is our original and the blue is the new. What happened was that the graph actually shifted to the left. So the red's the original, the blue's the new, and it shifts to the left. And you can see that with the anchor point as well. So normally it was here, but then it went over 1 unit. That's right there. And then finally 2 units. So based on patterns of graphs, and we saw these with lots of other graphs that we did this year, you can change those around. So if I were to put something, let's not look at it right now. So if I were to do -5 and then something like -7, this -5 tells me I'm going to shift the graph right 5 units, and the -7 tells me I'm going to shift it down 7. So let's just see if that actually did happen. And it did. So I go over 5 and then down 7. So again, this kind of acts like that, I don't want to say vertex, but it tells you how to shift. So that's what we kind of saw right here, and you might want to kind of make a sketch of some of those. But again, that's going to help you to determine what kind of X's and Y's you're going to use. If you know if it's going to shift right or left, and that's going to affect how the numbers start or where it starts. And one last thing I want to go back to is this right here. Do you see how this went up when the base was positive? But over here in number 2, it flipped. And that's because if we think about 1/4, that's really 4 to the -1. So that's actually flipping the exponent to be negative, which in turn moves the points around. The second part of this lesson has to do with solving equations, which are exponential equation is basically an equation that has a variable in the exponent. And we've kind of seen these sort of things before. Um, but sometimes they're easy to solve, sometimes they take some finagling. So we want to take a look at this. And really the object of this is to create the same base. So I have 25x equal to 125. Now if I try to do 25 squared, that's going to give us too large of a number. It actually gives us 625, which is way too big. And 25 to the first is only 25, so we know it has to be somewhere in between. So what I want to do is I want to create a similar base. I know that 125 can be written as 5 to the third power, while 25 can be written as 5 squared, and it's still raised to the x power. You'll see that the bases are the same, and once the bases are the same, then you can set the exponents equal to each other. When you have an exponent to an exponent, remember you multiply, so that just becomes 2x and equals 3. So then x equals 3/2. And if I were to plug that in, 25 to the 3/2 power, it would indeed equal 125. Number 6 is very similar, but we'll notice that there's a binomial in the exponent. So I just want to show you how we'll work with that. And we have a variable on both sides. So what's going to happen here is, again, I'm going to change this to 5 to the third, but now this is raised to the x power. 25 becomes 5 squared, but now it's raised to x minus 2. Because it's an exponent to an exponent, you need to multiply. So it becomes 2x minus 4, and that's going to equal 3x. And again, I can only do this now because the bases are the same. And then I'll solve like a normal equation. I will subtract 2x from both sides. So I'll get -4 equals x. So this is going to be 2 to the 2x equals 2 to the -5th. And then it's going to be 2x equals -5, x equals -5/2. I'm going to do something very similar with the last one. I know that 16 and 9 are perfect squares, so I can take out an exponent of 2 to both of these, so then it's 4/3. And if you notice that the bases are just reciprocals, I can do 3/4 to the x power equals, and then I can flip these around and change this to a negative, and then because that moves them around, so x equals -2. And wrapping up our last question, we have just a very slight word problem. It says the atmospheric pressure in millibars at an given altitude in meters can be approximated by the function, should be by, f of x equals 1038 times 1.000134 to the negative x power. And what we want to do is we want to find the ground pressure at ground level and then find the pressure at 8,000 meters. So at ground level, that would mean that it would be 0 because there's no height to it. So x would equal 0 at ground level. And all we're going to do then is just plug that in. When x equals 0, it will be 1038 times 1.000134 raised to the 0 power. Again, I would like you to put this in your calculator to make sure that you actually know how to use it correctly. And we approximately get 1,000, well, we do get exactly 1,038 millibars. And that's because anything to the 0 power is just 1, so that times 1 equals that. The next I want to find at 8,000. So I'm going to plug that number in with 8,000. And what we get for this is we get, and that should be a negative because it's negative x, we get 355 millibars.